Hi, welcome to Integral Calculus, and in this video we're going to be discussing about a Riemann integral in our lesson 3.1, which have a title Partition and Reimann Integral. And I'm gonna be discussing to you now this one and how it works. But before that, I'm going to show to you the theorem behind this one, which we're gonna be reading. It says that the concept of partitions or divisions and the formations of sums are initial steps in the development of a theory of integration. Here, we shall be discussing a way of choosing and forming sum that will give rise to the Riemann integrals or the definite integral. In the definition 3.1, it says that a partition D of A and B is a collection of points. It's a collection of points x sub 0 to the x sub n, such that A is equal to x sub 0 and less than x sub 1, less than up to x sub n, which is also equal to B. The norm of the size D, which is our partition, is the largest of the differences x sub I and x sub I minus 1, which our I is equal to a non-zero positive integer. Now, let our function AB maps into R, be a bounded function, and a partition D is equal to the set x sub 0 up to x sub n, a partition of A and B. If chi, this is chi, we name this one as chi, this symbol here is a chi. If chi sub I is the element of x sub I minus 1, x sub I for every interval, our x sub I minus 1 and x sub I, where our I is equal to a non-zero positive integer. This is a non-zero positive integer. This is a non-zero positive integer. Then we may form the sum of the product f of we form the sum of a product, this one, f of chi sub f of chi sub 1 of the difference is x sub 1 minus x sub 0 up to the x of f of chi sub n of the differences of x sub n and x sub n minus 1. Using the sums, if we're going to use the sum, sigma, it can be written as this one, or it's okay if we're going to write it like this or like this. It's okay, it's just the same. Now, this sum is called a Riemann sum. This can be called as Riemann sum. And the function of f is said to be Riemann integrable on A and B if the limit as a size of partition approaches to 0 of the summation of f of chi sub I of the difference as x sub I minus x sub I minus 1 as I ranges from 1 to n exist. Well, in this case, we write as this one. Now this is now our definite integral, which is the formula of our definite integral, which is better explained by the theorem or by the definition of the book. Now let's move to another definition. Our next definition in 3.1.2, we let our function f a and b maps into R be a bounded function. Then f is integrable in Riemann integral on a and b if there is a number I, such that for every epsilon, this is epsilon, greater than 0, there exists delta, this is delta, greater than 0, such that whenever D is a division of A and B with a size of a partition D, less than a delta, we have here are the form, which is the cardinality of D of the summation of f of g sub I of the differences of x sub I and x sub I minus 1 minus I as I ranges from 1 up to n is less than the epsilon. So that's it. Where our chi is the element also of the interval x sub I minus 1 and x sub I for every interval of this one in the partition. In this case, we say that I is the Riemann integral or the indefinite integral of f over the interval of a and b. Okay, this is gonna be the symbol here. It's what you've seen here. This is the symbol. We read that the definite integral of a function from a to b is equal to the definite integral of a function f of x dx from a to b is equal to I. So we call a and b as the lower and the upper limits. So our a is the lower limit and the b is the upper limit of integration. Now let's move to the remark, which is in every continuous function a and b maps into R is Riemann integrable in a and b. So that's it. In definition 3.1.3, if f is integrable on a and b, then we define this one. If we were letting our a to be the lower limit and our b to be the upper limit, then we can have a negative sign in here. Okay, and note this formula, which is very important, which can be written as the definite integral of f of x dx from a to b, which is equal to the differences of f of b minus f of a. Okay, that's all. The explanation of partition and Riemann integral, and if I'm going to better explain it to you now. Okay, I am giving you now I am explaining it to you clearly now, the theorem which we have discussed using our software Geogebra. This one, using this kind of software. Okay, using that kind of software, I'm gonna be discussing to you further. I'm gonna be showing to you how really the partition and the partition size work in Riemann sums. First is we must input a function. For example, if you have here a function, I'm sorry, asa naman ibutan na atong nawang. So I'm gonna be let's have a function here. First is let's have a function here. What if you have here a function x squared? Okay, that's function. Okay, we have here a graph, and we were gonna be putting a point here we were gonna be making a point, which is our partition is the point from here. Our partition is the point from, this is our partition. Any point lies in this line is called a partition, and the partition size is have another form to be used. Okay, so let's have, for example, we have here a point. Let's have here a point A. I'm gonna be putting an A in here. We're gonna be putting our A. Let's have our A here. But for example, we have our A in here, which is equal to our A will be equal to let's say we have our A which is equal to a coordinate, a point 0. Yes, we have our A in here, point, and let's have another A. Let's have another point in order for us to have a better size of a partition. So, for example, we have here 4. This is an impronto. So this is our point now. So we have our A point and B point. I'm sorry, mali. So this is our point here is 0. Okay, that's it. So we have our B and A point in here. It's what you've seen here. So we're gonna be zooming it out. So this is our A point is forming a point in here, and our B point is the 4 in the X. So our concern in here is to find the area of a curve. In ancient time, they are putting in solving the area of the curve is they are putting a rectangle like this one. They're drawing a rectangle and use the area of the rectangle and added all the rectangle they have drawn just to have the approximation of the curve. So they don't have any approximation of the curve during the ancient time. They're just approximating it using the rectangle they have. But because of this integral, we can now have the actual approximation. X of a point A and X of the point B and Rn. Okay, that's it. So we have this one. So our upper sum here is gonna be 48. This is 48. It is 47.99. So if we're going to round it off, it is 48. So this is the area being said by the upper sum. Just the upper sum. And our n here is 1. But if we're going to make our n to 5, then we have here a rectangle size of 5 rectangle. So that's what you've seen here in upper sum is we have here the over approximation because it is an upper sum. But if we're going to have a lower sum, we can also have an under approximation of the area of the curve, lower sum. Let's try to have a lower sum. Lower sum, it's just the same input of what you've seen here, upper sum, X of A, oops, next will be our X of B, comma, N. And that's it. This is our lower sum, and we're gonna be changing the color. This is our red. Okay, that's it. Our lower sum is the red. So as what you've seen here, the lower sum is starting from this is starting from this side up to this one, and from this partition here, from this one to this one, and starting from the left side. And our upper sum is starting here is starting from the right side, which is our upper sum, starting from the upside up to the last of the end of the curve, end point of the curve, which is in 16 here up to this one. Then this is the partition. This is the size of the partition, which is each rectangle has a size of a partition, which we were going to find the area of each rectangle. Then the area of this first rectangle, the second rectangle, up to the fifth rectangle is where we're going to add it one to have a better approximation of the curve. but actually the actual approximation of the curve is this one: integral f of x of n, that one, b. This is the actual approximation of the curve. 21. So we have here the actual approximation of the curve, which is 21. From if we're going to integrate that x sub 2, we can have here 1/3 x sub 3. From a, which is r1, from 1 to 4, we can have our answer 21. This is the real integral of that. It is far from the actual answer because we have here 16 in the lower sum, then the area that they have got in the upper sum we have 25. So it is much. But if you're going to find the average of that one, to obtain the approximation, so we have here 25.68 plus 16.68 divide 2, we have here 21.18. so our actual, we have here our answer, which is 21.18, but in here we have here 21, so it is very actual if we're going to calculate the average of the upper sum and the lower sum and finding the integral. So the actual integral, it is good to have software to better explain to you how integration really work in finding the area of a curve. Okay, and that would be all. I have here also, I'm going to show it to you if the we have also here our n, which is the rectangle. If we're going to let our n be equal to 10, our rectangle also will be move into 10 rectangle. So the more our rectangle will become tiny, or the more our n increases, also the approximation also into the actual approximation will increases also. So if we will letting our n to become 100, so look at this one. If we're letting our n to become 100, so this one. If we're letting our n to become 100, so our 100 n will be that one. Okay, the real approximation will found if our n will be into the infinity. If we let our n to become infinite, so the approximation will be correct of checking the area. And that would be all. Thank you.